Okay, I am back now with part 2 of the unit circle video and talking about right triangle trig as it relates to the unit circle. So a quick review here. You may remember that the Pythagorean theorem, you may have learned it as a squared plus b squared equals c squared. Well, we won't always have a, b, and c as values. So let's instead think of it as leg squared plus leg squared equals hypotenuse squared. Then I'm not looking for, hung up on A, B, and C, and I can use this theorem in a really versatile way. Remember that theta is the angle. Theta is the way that we talk about angles. It's the Greek symbol that we use to designate the angle that we're looking at. When I talk about right triangles, whatever angle I'm using, the side opposite has a name, the side adjacent to that has a name, and then of course the hypotenuse is always the side opposite the right angle. Just going over this. This is the beginning, the precursor to the idea of SOHCAHTOA that many of you were talking about the other day. When I talk about right triangle trigonometry, if this is my angle theta, this side, the longest side, would obviously be the hypotenuse. It's opposite the right angle. Opposite the angle that I'm interested in would be the side opposite, of course, and then next to it would be the side adjacent. Here's my theta, here's my hypotenuse, opposite the right angle, opposite theta, the opposite side, and next to theta, the adjacent side. Okay, basic review of trig here. Now, we talk about SOHCAHTOA. There are lots of different ways to remember and memorize this, but what I want you to remember mostly is that sine is the ratio of the opposite side over the hypotenuse. So the cosine is the ratio of the adjacent side over the hypotenuse, and the tangent is the ratio of the opposite side over the adjacent side. When I talk about, we'll talk about reciprocal trig identities later on in the notes. For now, though, let's just work with basic sine, cosine, and tangent. And I want to skip a little bit from these quotient identities down talking about the unit circle. So I'm now on page 10, and I want you to remember the special right triangles that we talked about a few days ago. I want to think about how these triangles got placed inside of that unit circle, right? With a 60, 30, 90, a 45, 45, 90, and a 30, 60, 90. Not the most accurate picture, but you get the idea, right? Each of these triangles, the 30, 60, 90, now with a radius of 1, I can figure out the length of the other sides. You could use SOHCAHTOA, but let's instead use those ratios that we know, right? If 1 is the hypotenuse, and the hypotenuse is known as 2x, then the side opposite 30 is going to be x, and the side opposite 60 is going to be the square root of 3 over 2. So if I'm interested in, okay, what's the sine of 30 degrees, I want the side opposite, that 30-degree angle, over the side adjacent. But they're in terms of x right now. Let's solve for x, and let's see what those lengths are going to equal. 30 degrees in here. If 1 is equal to 2x, then x is equal to 1/2. So the short side is 1/2, and this side here is going to be the square root of 3 over 2. And I made a little error before. I got ahead of myself. The ratio here is actually x square roots of 3. Okay, so back to this triangle here, the 30, 60, 90 triangle. Whenever I'm talking about a unit circle, I'm talking about a radius of 1, and these are going to be the lengths of the legs, 1/2 and square root of 3 over 2. So if I'm asking about the sine of 30 degrees, the sine of 30 degrees is going to be equal to the opposite over the hypotenuse. That's going to be equal to the side opposite, okay, 1/2 over the hypotenuse, which is 1, it's just going to be 1/2. When I'm talking about sine, I'm really talking about the y value. So the sine, when you're talking about the unit circle, is equal to the y value, just that side opposite. Now, what about the cosine of 30 degrees? Okay, well, what about the side, if I'm talking about cosine of 30, I'm talking about the adjacent over the hypotenuse. So what I'm talking about then is the side adjacent would be the square root of 3 over 2 over the hypotenuse, which is just 1. That's the square root of 3 over 2. So what you notice here is that the cosine of 30 is the x value. So the cosine in the unit circle is just the x value. It's that horizontal distance. These two ideas, that sine is y and cosine is x, are underneath this entire unit circle. Because once I put a triangle in here that's got dimensions of 1/2 and square root of 3 over 2, that point on the unit circle in the coordinate plane has the coordinate point of the square root of 3 over 2 comma 1/2, because I go over the square root of 3 and up 1/2 of a unit. All right, I skipped around a little bit and I moved through this quickly. Let's look at the 45-degree angle now with the triangle that's here. I'll just do a different color. The triangle here that's in red up here. This, and I'll continue to write in red. Well, if I know that the unit circle has a radius of 1, I can set square root of 2 over 2 equal to 1. What I end up with, if I divide both sides by the square root of 2, is solving for x, I get, rationalizing that, I get the square root of 2 over 2 is equal to x. That means that the length of each of those sides is the square root of 2 over 2. What that means is that the length of those sides of that right triangle, 45, 45, 90 triangle, is square root of 2 over 2, comma square root of 2 over 2. That gives me the coordinate for that point on the unit circle, because I'm going over by that distance of root 2 over 2 and up by that distance of root 2 over 2. So now that point has a point in space. It's not only got an arc length and an angle measure, but it's also got a very real coordinate point, remembering that that's the center of the xy axis. I'm just moving left and right a certain number of units based on the lengths of the legs of that triangle. So if I want to know what the sine of 45 degrees is, it's the opposite over the hypotenuse. Well, it's the square root of 2 over 2 over 1. It's just the square root of 2 over 2. It's equal to the y value at that point. Okay, and cosine of 45 degrees. Well, I bet you can guess what it's going to be. If it's the adjacent over the hypotenuse, the length of the side adjacent to this angle, theta, is the square root of 2 over 2, and the hypotenuse of that right triangle in the unit circle is 1. So the cosine at 45 degrees is the square root of 2 over 2. It's just the x value. Ta-da! Hopefully, and this is the take-home message here, that when I'm talking about the unit circle, what I'm getting at is that I've got these special right triangles inside the unit circle. And due to the length of their legs, the points that they correspond to on the unit circle have real dimensions and real lengths when the radius is 1. Right? Root 2 over 2, root 2 over 2. We talked about how if this is theta, the sine is the opposite, so that's the y value over the hypotenuse, which is 1. And the cosine, excuse me, they're not equal. And the cosine of theta is going to be the x value, right? The horizontal distance, the side adjacent. So if you take out nothing else from this, I want you to know that sine means y, the vertical distance, the side opposite theta, and cosine means x, the horizontal distance, the side adjacent to theta. Okay, so that's it for now on this video. More to come in a little while.